All right, so talking about types of chemical bonds, we're going to start by talking about the ionic bond. Now, in ionic bonds, electrons are donated. Now, what happens, we start with sodium, the common ion, and chlorine. Sodium is a group 1 element, meaning it has one valence electron. Chlorine is a group 17 element, meaning it will have 7 valence electrons. Now, sodium desperately wants to get rid of that valence electron to become a noble gas and have a full outer shell and be stable. Chlorine wants to do the same thing, except for chlorine is going to do that by gaining an electron to have the configuration of argon, another noble gas. So what's going to happen is, through that great difference in electronegativity, chlorine is going to steal an electron from sodium. Now sodium has a positive charge. Chlorine, gaining an electron, has a negative charge. Those two are attracted to each other through electrostatic forces, just meaning opposite charges attract. So now that we have two ions forming, let's rewrite this ionic compound that we now have using the Lewis dot structure. Lewis dot structure simply shows valence electrons. So now we have an ionic bond right there and an ionic compound. So ionic compound has just formed. Now an ionic compound forms between a metal, sodium, and a non-metal in chlorine. Now covalent bonds share electrons. So let's look at oxygen and oxygen. We're going to do the Lewis structure, showing the valence electrons for oxygen, which has 6, according to your periodic table, showing that it is in the 16th group. Okay, so in order to reach their octet, they're going to need to share not one, but they're going to need to share 2 valence electrons. So let's see what that looks like. Here we have oxygen and oxygen. Put those valence pairs over here. And in between them, we're going to have 2 lines indicating a double bond. Each one of these lines represents 2 shared electrons. Okay? So now each of them has 8 if you count the sharing, the 4 that are sharing as well. Okay, so oxygen has reached its octet. It's now stable as O2. And covalent bonds often is between 2 elements that are the same. What we call these is diatomic elements. And they only exist in nature as diatomic elements because they're extremely unstable otherwise. Another covalent bond we can look at would be It's oxygen again. And we're going to use hydrogen as our example here. Hydrogen has 1 valence electron. Oxygen has 6. And if you count the bond here as 2 shared electrons, hydrogen has 2, filling its outer shell, and oxygen has 8, reaching the octet and filling its outer shell. Now, oxygen is more electronegative than hydrogen, so it's going to be partially negative here and partially positive on these sides. So we have a polar molecule where these electrons are being drawn closer towards oxygen, creating a partial positive and partial negative polar molecule. Now, I forgot to mention that covalent bonds exist between a non-metal and a non-metal. Metallic bonds, on the other hand, is the extreme sharing. Extreme sharing, well, let's change that, of electrons. Okay, so in this case down here we have iron. We've got an iron metal, and in it I've drawn in some electrons here. These electrons are fluid and they move around a lot. Okay, they're not bound to any one atom. So in a metallic bond, we call it a sea of electrons. So metals like to share with other metals, creating this sea of electrons. They're overlapping, these electrons are. They're not fixed to any one atom. This is what gives metal its malleable property. Allows it to bend and form, because the electrons can move very easily from atom to atom. And because of these, the sea of electrons and these free-flowing, I'm going to write free-flowing in here. It's a good descriptor. Free-flowing electrons. Because these free-flowing electrons throughout the metals with the metallic bonds are very good at conducting electricity. So I think it's pretty helpful to imagine bonding as a spectrum. So on this side of the spectrum, over here, we have a covalent bond. And on this side, we have an ionic bond. So as the electronegativity difference, as our END increases here to here, we're going to be more and more ionic. Okay, that means that the one atom is so much more electronegative that it's going to pull in those electrons closer to itself, creating that polarity that we're looking at, up into a point where it's not polar anymore, it's simply ionic, and it's not sharing that electron anymore, it's actually stolen the electron. The more electronegative element has stolen that electron from the less electronegative element. So on this side, both atoms are both participating in bond are roughly equal in how badly they want those electrons. And over here we have very big difference in electronegativity. Okay. So just understanding that and looking at the periodic table, we're going to look at different groups here. We're going to start with the alkali metals. The alkali metals want to lose electrons. Okay? So with the alkali metals, we get potassium +1, lithium +1. Okay? They're usually going to be +1 cations. And then if we look at the alkaline, they want to lose 2 electrons. So here we got magnesium 2+, calcium 2+. Now the reason, again, why they want to lose 2 electrons is because they want to be noble gases. Okay? On the other side of the spectrum here, we're going to look at our noble gases. They have a full outer shell. Okay? So they're not going to gain or lose any electrons. And the halogens here, our halogens, they need 1 electron. Use this. So they're going to add an electron to get their full outer shell, their octet, and they're going to be fluorine, for example, at -1 and chlorine at -1. And then this group 16 here, they want 2 electrons. Okay, so some examples of these elements are going to be oxygen, which is going to be 2-, or sulfur, which is going to be a 2- anion. So just a quick review of bonding ionic and covalent compounds and ionic and covalent types of bonds. With ionic, we have an electronegativity difference of 1.7 to 3.3. Those are going to be bonds that form between metals and non-metals. The electronegativity difference is so great that the anion is formed, pulls, its electronegativity is so great that it pulls the valence electron from what becomes the cation. Covalent bonds form between non-metals and non-metals. And we have two types of covalent. So the first thing you do is you figure, is it a metal or a non-metal? And if it's metal or non-metal, you know. If it's a metal and a non-metal, you know that it's going to be an ionic compound. An ionic bond is going to form. If it is between a non-metal and a non-metal, then you have to decide, is it going to be a polar or a non-polar covalent bond? And the way that we do that is, that's when we start looking at the END. So our polar covalent bond is going to form between two elements that have an electronegativity difference of 0.3 and 1.7. Polar molecules are going to be asymmetrical. They're going to be asymmetrical because one of those elements is going to have a partial negative and one's going to have a partial positive charge. So we have partial charges. What this means is that the more electronegative element is going to pull the electron closer towards it, increasing the electron density around the more electronegative element. So the electrons are going to be unevenly shared. Uneven sharing of electrons, okay? And our nonpolar element, our nonpolar bond, our nonpolar covalent compound is going to be symmetrical. And that's going to fall in between, we're going to put an NP right here. That's going to fall in between 0 and 0.3. Okay, it's going to be symmetrical in nature because the two elements have similar electronegativity, and so they're going to share. They're going to evenly share those valence electrons. Okay? And there's not going to be any partial charges in a nonpolar covalent compound.